So this section in the book is called Estimating with Finite Sums. You guys know what estimating means. What does finite mean? It has an end. It's countable. So we can it has an end. It might be like a really long process. It might be fairly quick. But we're going to estimate something that's infinite with something that's finite. So we're going to try to get close to it. And you might be able to guess after I say that we're going to go from the finite to the infinite by using what? Starts with an L. Limits. Yes. Okay, remember, we're not using derivatives anymore. We're moving away from those. But we're going to use a limit to go from finite estimations to exact answers using limits. So the whole idea of this chapter is, or at least this section of the chapter, is to estimate something. Now, at the beginning of the year, we talked about the two major problems in calculus. The two things that back in the 1700s, they were trying to do these two things and come up with processes that would work for really any type of function. The first one is what we've been doing. It's the tangent line problem. And the tangent line problem is essentially finding the equation of a tangent line. Really, the calculus part of it is not the equation of the tangent line, but finding the slope of the tangent line. So if we pick any point, we can find the instantaneous rate of change at that point. Before calculus methods came along, we could really only estimate that slope. We could get close to it, but we didn't know exactly how to find it. So we've spent the last couple of months talking about that, what we do to find the tangent line, and then how to use it, what uses it has. The other major problem in calculus is what's called the area problem, and as you can imagine, we're trying to find an area. Usually finding an area is pretty straightforward. We know a bunch of area formulas, but if we wanted to find the area of a region like this, there's no geometric formula that tells us, okay, well, there's a parabola, here's how we find the area under the curve. We'll talk in a little bit about why finding the area is important, but this was a really important idea for a lot of reasons. It has a lot of really good applications. So we want to find the area under this curve. Now, what kinds of shapes do we know how to find the area of? Triangles, squares. The two most basic ones are squares. In fact, we measure area with squares. We call them square units, right? So if we were going to measure the area of anything, we call it square units, whether it's a square or not, or whether we could cover it with squares or not. So squares and rectangles are really the two basic ones. And the formula for the area of a rectangle actually comes from the area of a square. The formula for the area of a triangle comes from the area of a rectangle. The area for a parallelogram comes from the area of a rectangle, along with something called Cavalieri's principle. And we'll talk about Cavalieri's principle later on. But basically we just take a rectangle and we shift it over. So it's really easy to find the area of a rectangle or a square. It's not as easy to find the area of a curved shape. It wasn't, well, I mean, it was like 2,200 years ago, but Archimedes was the first one to find the area of a circle accurately. But he couldn't do it. He couldn't do it easily because it's not a square shape or a rectangular shape. So we're going to talk about how we're going to solve this. Let's talk first about why we would want to solve something like this. Let's say I give you a graph here. Along the vertical axis, we have velocity measured in miles per hour. Along the horizontal axis, we have time measured in hours. And we'll just say this is the velocity function of a car driving over a period from 0 to 5 hours. What could you tell me about this car? Anything?
65 miles an hour.
Okay, it's driving at a constant speed of 65 miles an hour the whole time. Okay, I agree with that. That's really the only thing this graph tells us, right?
No.
That the car drives from, well, it's the only thing this graph tells us directly. From t equals 0 hours to 5 hours, it's driving 65 miles an hour the whole time. Now, indirectly, we could use a little bit of math and a little bit of our knowledge to compute something else, what else could we figure out? How far it's gone, right? Well, there's a formula in physics that that ties the velocity and the time and the distance. And what is that formula? X equals, yeah. So, wait, x equals vt? Yeah. So distance traveled is equal to the velocity times the time. Okay? You guys remember that formula? Or you know that formula? Those of you that are not taking physics, do you know that formula? No. Okay, so v is velocity, t is time. So if you take how fast you're going times the amount of time that you go that speed, you get the distance that you traveled. Okay, and actually we should be a little bit more specific here. X is usually referred to as a position, and what we're really looking at here is the change in x. It's not that important right now, but it will be important later. So it tells you how far you've gone. So that means that if my position is, say, 100 miles away from some origin here, then in the end we're gonna end up, well, we can figure out where we are and how far we've gone. So in this case right here, in this problem, how far did the car travel over the 5 hours? 325. So the distance it traveled would be the velocity, which is a constant 65, times the time, which is 5. This is 65 miles per hour. This is 5 hours. The hours cancel each other out, so we get, what'd you say, 325, what? Miles. So the car traveled 325 miles. Well, if you look at the picture here, and remember we're answering the question, why would we want to find the area under the curve? If we look at the picture here, what we have is a rectangle. And that rectangle has dimensions 5 hours by 65 miles per hour. So when we use this formula here, what are we actually doing? Geometrically, what are we doing? We're finding the area of that rectangle, right? So when we take 65 times 5, we're finding the area of this rectangle. So in this case, when we have a graph of velocity versus time, finding that area, finding the area under the curve. Now it's not really a curve, but a straight line is actually called a curve still. So finding the area under this curve tells us how far the car went. Well, the same thing would be true if we had this graph. If I tell you that the velocity of the car on this axis compared to the time that it's traveling on this axis is this graph, we looked at this graph already, then if I ask you how far the car travels in 16 hours, what we would want to find is that area there, the area under that curve, and that will tell you how far it went. So whether it's a rectangle like it was in the last graph or whether it's a curve like it is in this one, if we find that area, it's going to tell us the change in its position, how far the car went. Does that make sense? Now, if you remember, when we were talking about derivatives, we started with position, and then we said the derivative of position is velocity, and then we also said the derivative of velocity is acceleration. Well, if we look at this here, what we have is the velocity graphed with respect to time, and when we find the area under the curve of the velocity, we get the position. So when we take the derivative of position, we get velocity. When we find the area under velocity, we get back to the position, or at least the change in the position. So the area under the curve is tied very closely to the derivative. It's actually the opposite. Yeah, antiderivative. Let's talk about how we might find the area under the curve. Like I said, we don't have any formulas to find the area under just a generic curve, at least not from geometry. In geometry, we know how to find the area of rectangles. So what I've done here is I've approximated the area under the curve with rectangles. Does everybody see what I did, how I did that? So I just broke it up into a bunch of rectangles. And so what I'm trying to do is I'm trying to approximate this area right here, the whole area under the curve, by breaking it up into rectangles. Now, there's a problem with that. What's the problem? I think it's a fairly obvious problem.
They're triangles.
Yeah, there's a bunch of, they're not really triangles, but they kind of look like triangles. But there's a bunch of gaps there, right? So when I do this, when I find the area of these rectangles, I'm going to be missing something. I'm going to be missing this area here, and this area here, and this area here, and you get the idea, but it's not quite getting the whole area. So what could I do? What could I do to make it more accurate? Well, hold on. Let me back up. Sorry, I'm getting ahead of myself here. This is a pretty close estimation, a pretty close guess. It wouldn't be exact, but it would be close enough, maybe in some cases. How would I find the area of these rectangles? What would I need to know first? Let me give you a hint. We need to know what this function is, don't we?
Yes.
We would need to know what that function is to find the areas. Now, once we know that function, let's say I wanted to find the area of just this rectangle here. What would I do? Okay, I would plug in 8, so Joe and Alec are both on the right track here. The y value here for that point, and I'll come all the way over here, is going to be f of 8, right? And that y value is also the height of the rectangle. So that height right there is going to be f of 8. So the height of the rectangle, we can use the function to figure it out. What about the width of the rectangle?
2.
It's just 2. What do you notice about the width of all of these rectangles? 2. Now, I'm going to talk about a few different ways that we can use rectangles to estimate here. It's easier to use rectangles that all have the same width, but it's not necessary to use rectangles that all have the same width. And we're going to do an example together later where we're going to use rectangles that don't have the same width. So to find the area of just that rectangle, we would just say f of 8 times 2, right? And if we wanted to find the area of all of the rectangles added together, we would do what? Do that to all of them. So we would do 2 times f of 0, 2 times f of 2, 2 times f of 4, 2 times f of 6, 2 times f of 8, all the way up to 2 times f of 14. Now, as you guys said, we're missing some stuff. We don't have the full area. We don't have the whole area. So our area is going to be an under approximation. What's something we could do to make it more accurate?
Find the tangent line in the middle of that and do a triangle.
Wow, that would be a lot more accurate, but also a little harder than what we're looking for. Good idea, though. Abdallah, what do you think? Okay, good. Jeremy, you said that too, right?
Yeah.
So instead of using, what I have here is 8 rectangles over an interval of 16 units. What we could do is break it up into maybe 16 rectangles. Break it up into more rectangles. Okay, that would be something else. Now if we did that, and I'll just kind of draw in a few of them here. I'm going to start on the right side. So if we did that, we would get a picture like this. Let me fill this in too. So we would basically be getting that extra space there, but it's still going to be an under approximation, right? You guys agree? Okay. What if I wanted to go the other way? What could I do to get an over approximation of about the same amount? I'll give you a hint here. Over the interval from 8 to 10, I'm going to go back to the 8 rectangles. Over this interval right here, I used the left endpoint as the height of the rectangle. I could use the right endpoint, right? So if I did that, what I would be doing is I would be getting areas that looked like this instead. So I would include that whole area there and this whole area here. What's that?
If you did both, could you find the average?
Okay. If we did both, we could find the average, and actually the average would give us the area of what's called a trapezoid. You guys know what a trapezoid is, right? So it would give us this area here. Now it's hard to see in this picture because it's not curving much, but it wouldn't be exact. And the reason it's not exact is because when we find the average, we're finding the areas of trapezoids. They have straight lines here. The trapezoids do. And these are not straight lines. It's actually curved, so it would still be slightly an over approximation, but it would be a lot closer, wouldn't it? Okay? Do you think we have to use a right endpoint or a left endpoint? No, we could actually use any point on the interval. So if I said between 8 and 10, instead of using 8 as the height, or instead of using 10 as the height, maybe I'll use 9. Maybe I'll use the midpoint. So I would figure out what the value of the function is there and find the area of this rectangle. Okay, lots of ways we could do it, right? Of the three, I mentioned 4 there, I guess. Of the 3 with rectangles, which one do you think is the most accurate? The left endpoint, the right endpoint, or the midpoint? Midpoint. The midpoint is more accurate here. Do you think the midpoint's always going to be more accurate? No. It really just depends on what the curve looks like and how big the intervals are and what it looks like within the interval. So we can kind of play around with it and see what happens when we use the left endpoint, the right endpoint, or the midpoint. That would be one way to try to gain some accuracy. Another thing is what Abdallah and Jeremy said is we can use more rectangles. So break it up into smaller rectangles that fill the gaps a little bit better. So there's lots of ways that we can try to approximate this area much more accurately. So there's 3 different ways that we're going to do it. You don't need to draw the pictures. You can if you want. If you really want, I can print this page out for you and you can have the pictures drawn for you. But we're going to use what's called LRAM. LRAM stands for Left Rectangular Approximation Method. Right Rectangular Approximation Method, which would be RRAM, or MRAM, which would be Midpoint Rectangular Approximation Method. For this particular curve, like we said, the midpoint is probably going to give us the most accurate. If you look at it here, I know it's kind of hard to see, but we have a little extra there and a little bit not enough there, and they kind of balance each other out. So the midpoint is going to be more accurate in this case. Depending on what the curve looks like, though, it may or may not be. So what I want to do is just go through a couple examples where we're going to use each of these and kind of interpret what's going on. All right, any questions about that? All right. This problem was actually a bonus question on the Chapter 3 test. I know a lot of people didn't even have time to get to it, which is fine. That's kind of why it was bonus, and also because we hadn't talked about this yet. But it was an introduction, actually, to what we're doing right now. So what we have in this problem is we have water flowing into a water tank over a 2-hour period. The rate that the water is flowing in is measured right here. So at noon, the water is flowing in at 12 gallons per minute. At 12:30, it's flowing in at 4 gallons per minute. At 1, it's flowing in at 5 gallons per minute, and so on. So that gives us the rate the water is flowing. What we want to do is approximate the total amount of water that goes into the tank during this time. The first thing I would probably do to do this, some people did it, some people did not, and like I said, a lot of people didn't even have time to do it. But the first thing I would do is just draw a graph of what's going on here. So since we're going from noon to 2 o'clock, I'm just going to call this axis T in hours. And so 0.5 would be 12:30, 1.5 would be 1:30, and so on. And then I'll graph the rate along the y-axis. So we'll call that flow in gallons per hour. I think it was gallons per minute. It's going to be important. One thing I probably should change right now, since we have gallons per minute here and we have hours here, I probably should change one of them. Which one do you think I ought to change? Yeah, instead of hours, let's use minutes there. So we'll say that's at 60 minutes starting at noon. That's at 120 minutes starting at noon. So that would be 90 and 30. So this time right here at 90 minutes would correspond to 1:30, right? And then if we graph what's going on here, the highest it's going to get is 5, so I'll put that on there. That's going to be 5. It's not very even. It's going to bother me. Okay, so at noon it's flowing at 2 gallons per minute. At 12:30 it's flowing at 4 gallons per minute. At 1 it's flowing at 5. At 1:30 it's flowing at 5. At 1:45 it's flowing at 3. And at 2 o'clock it's at 0. Okay, so that shows the flow. What we want to do is guess how much water flows in during that time. Now here's what I saw most people do, most people that attempted this, and I really like this. What you said is over the first 30 minutes we'll just assume that, say it's flowing at 2 gallons per minute. So what you did is you said 30 minutes times 2 gallons per minute, and that's going to give you 60 gallons that flowed in during that time. And then over the next time interval from 12:30 to 1, maybe we'll use the 4 here, and we'll say that it flowed 4 gallons per minute over that time interval. So for 30 minutes it flowed at 4 gallons per minute. And then the next interval we'll say that it flowed at 5 gallons per minute for 30 minutes. And then the next interval is how long? It's only 15 minutes. And again, if we stay consistent here and we say that the beginning of the interval is what we're going to use, we'll say that's 5 gallons per minute. And then the last interval is 15 minutes at 3 gallons per minute. Yes?
So would that feel like using the left?
It would. That's exactly right. So those of you that did it this way, which, like I said, a few of you did, Alec is exactly right. That would be using the left rectangular approximation method. And just to show in the picture what we're doing here, what we would be doing is drawing these rectangles right here and using those rectangles to approximate how much water flowed in, right? Now, I said it's usually more convenient if we keep the time intervals the same or keep the widths of the rectangles the same. In this case, since we have data broken up here, the 30-minute period was broken up into 2 sections, we'll go ahead and break it up also. It doesn't make sense to make this a 30-minute interval just because all the other ones are 30. So this is a case where the intervals are different widths. And we can get a more accurate answer this way. Now, if you did it this way, do you think this would be an over approximation or an under approximation? Why? That was one of the questions that was asked here. Why would you think that it's under approximation? Okay. What I would do to answer this question is draw a picture of what the flow might actually look like. It's not going to be a stair-step graph like this, but it's going to be more of a smooth curve, more than likely. So if we draw a smooth curve that goes through all of those points, it would be an under approximation if we think that the gaps here that are missing are bigger than the extras out here. It would be an over approximation if we think these would be bigger than the gaps in here. I think you guys are right. I think this would be an under approximation because it looks like these two these 2 parts that are left over would be smaller than these 2 here. Do you guys agree with that? Okay. We can do the math to figure it out. Did anybody add all these up? No? Okay, that's fine. We could do the math. That's kind of irrelevant here. You should be able to do that, but we would get 60 and 120 and 150 and 75 and 45. If we add them all up, we'd get 450. So 450 gallons. So by using the left rectangular approximation method, we would get 450 gallons. Does that make sense? Okay, what if we wanted to use the right rectangular approximation method? What would be different about all this? Well, hold on. Let's talk about the math part first. What would be different about the problem that I just did?
The flow that we used.
Yeah, so instead of using 2 for the first half hour, we would use 4. And instead of using 4 for the second half hour, we would use 5. And for the third half hour, we would use 5. For the next 15 minutes, we would use 3. And for the last 15 minutes, we would use 0. And so we get 120, 150, 150, 45. So we get 465 total. And what do you think? Would that be an over and under approximation? I think probably an over approximation. If we draw the rectangles that would be represented here, they would look like this. And that would just be a flat line there. And the curve would probably look something like that. I missed it, but you get the idea. Actually, let me fix it, because it's kind of important with estimating. It looks like these right here, these extra pieces are bigger than the gaps here, so that would probably be an over approximation. Does that make sense? Yeah.
What if you took like the over approximation and the under approximation?
And average it?
Yeah.
And that's actually something that we'll do. Like Alex suggested with the left and the right, with that one that we were looking at before, we knew the left endpoints gave us an under approximation and the right endpoints gave us an over approximation. So if we average them, we should get something that's a little bit closer. In that case, and actually we can look at the concavity to decide whether it's going to be over and under. In that case, since it was concave up, we still had an over approximation, but it was a lot closer. In this case, if we use the average, we would get an under approximation, but it would be a lot closer. So if we were to average the left and the right endpoint, then we would be able to get a much closer guess at what was going on. What was the first one? 450? What it was? Yeah, the first one was 450. The second one was 465. So it's probably going to be somewhere between 450 and 465. Yes?
Is there some way of like figuring out exactly?
So in this particular problem, there's no way to know exactly how much, and the reason is, let me back up here to this. The reason we couldn't figure out exactly what it is because we don't know exactly what the function looks like. It's possible that we measure a rate of 2 at noon, but the rate actually does something like this. So since we only know data at those points, we don't know exactly what the function looks like. There's no way we could for sure. Now, what we could do, if we wanted to get even more accurate, and we've mentioned 4 ways. We've got LRAM, we've got RRAM, we've got MRAM. We couldn't use MRAM here. We couldn't use the midpoint because we don't know what the rate is halfway between 12 and 1230. But we could use the trapezoid one that I talked about, which is the average of the left and the right. And that would give us a more accurate answer. Or you can actually use polynomials to approximate it. And we're getting more accurate with it, but then we're also getting to things that would be more complicated. But we could say, well, that kind of looks like a parabola. So I'm going to use a parabola to approximate this curve, and then see what the area is underneath that parabola. The only problem is we don't know how to find the area under a parabola yet either. So the answer is we can get pretty accurate if we make some assumptions, but we can't know for sure. Good question. Okay, let's do an example, and I want to do this one together. I want you guys to kind of work through it with me. We're going to do the left endpoints, and then I'm going to have you do the right endpoints and the midpoints on your own. Okay? So we have this function. F of x is x squared. We're looking at the interval from 0 to 4. And we want to evaluate LRAM 4. What do you think this little 4 here means? Yeah, we're going to use 4 rectangles. So we're going to use LRAM 4 to approximate this area. We're not going to get it exactly, but we're going to approximate it. All right? Does that make sense what we're trying to do? All right. Like I said, we'll work this one together, and then I'll ask you to do the other 2 on your own. The first thing we want to do is figure out how wide each rectangle is going to be. Now, this is pretty simple. I think everybody could just tell me what the answer is right off the bat. How wide is each rectangle going to be? going to be 1 unit, right? You guys agree with that? How did you figure that out? Yeah, the width of the interval is 4, so we can figure out what the width of the interval is by doing 4 minus 0, or this would be b minus a. So we could do the width of the interval divided by the number of rectangles, divided by 4, and that's going to give us a width of each rectangle of 1. We're going to call that delta x. Anyone want to guess why we call it delta x? Yeah, that's the change in x for each rectangle. So each rectangle is going to have a width of 1. So then, once we know how wide each rectangle is going to be, we want to figure out where the rectangles are going to be specifically. So since we're going from 0 to 4, I'm going to put points at 0 and 4 on the x-axis. Where are the edges of the rectangles going to be? This is another pretty easy one. 1, 2, and 3, right? Now, let's say that delta x was something like 2/3. What would I do to figure out where those edges are going to be? Start at 0 and add 2/3 over and over and over again. So it would be at 2/3, 1 and 1/3, 2. 2 and 2/3, 3 and 1/3, 4. So we could, if we were going to divide this into 6 rectangles, our delta x would be 2/3, and then our rectangles would be split up every 2/3 along the way. Okay, if we were on the interval from, let's say, 1 to 5, we would start at 1 and then add our delta x on over and over again. Does that make sense? Okay, so let's go ahead and draw in our rectangles here. Now, where am I going to put the tops of the rectangles? On the left end point. So this first rectangle here actually isn't a rectangle at all, is it? Since I'm using the left end point, the top of the rectangle is just going to be along the x-axis there. That's unfortunate because we're not going to get any area for that one. The next one is a little bit better. We get some area there. The next one is there. The next one is going to be there. And we're actually not going to use the value of the function at 4 itself. So now, again, what we're looking for is the area inside of these rectangles to approximate the total area under the curve. Does that make sense? All right. I'm going to clear some space here so I can work. What's the height of this rectangle going to be? How do we know that?
0 squared.
Yeah, we put our left endpoint in, and f of 0 is 0. How about the height of this one? It's going to be 1 because, yeah, f of 1 is 1. How about this one? It's going to be 4 because f of 2 is 4. And the last one, f of 3, we're using the left endpoint again, is 9. Okay, so those are the heights of the rectangles. How wide is each rectangle?
1 unit.
1 unit. Now, here's a shortcut that's going to save you time when you're doing more complicated problems. If I want to find the area of each one of these, I'm going to take 0 times 1, 1 times 1, 4 times 1, and 9 times 1. So I'm taking each one of these times 1. Now, if it's 1, it's kind of pointless. But the total area then, and I'm going to call this LRAM 4, so I'm going to say what it is that I'm finding, is going to be the width of each rectangle times the height of all the rectangles added together. So basically I'm factoring out the width of all of them, and then I'm going to add in all of the heights. And what do I get? So by breaking this up into 4 equal sized rectangles where the left endpoints are the height of each of the rectangles, we get an area of 14 under the curve. So here's what I want you to do then. Same thing, except use the right endpoints. All right, let me point a few things out here in this formula in particular. First of all, to get the height of each rectangle, now we're using the right endpoint. So we're putting the x value of the right edge of each interval, each sub-interval, into the function to figure out how high the rectangle is going to be. And then we multiply by delta x here. So if we were going to try to build a formula for this, for RRAM 4, it wouldn't really matter what interval we're on. We're going to take delta x and we're going to multiply by, in this case, and I'm going to have to kind of put stuff in here, f of 1 plus f of 2 plus f of 3 plus f of 4. So this is kind of a formula that we're using here where the 1 depends on where we start and what our delta x is. So we start at our left endpoint and add on delta x here. And then this 2 here, we start at the left endpoint and we add on delta x twice. And the third one, we start at the left endpoint and we add on delta x 3 times. So you can kind of see the beginnings of a formula here, right? At least if I write it that way. Honestly, I'm going to show you a formula. I'm only going to show you the formula for the left endpoints. The formula is not that important to know. You just need to know how to do it. It's a lot easier to just kind of work it out from a picture or from information that's given to you than trying to plug stuff into a formula that doesn't really have immediate meaning. So like I said, I'm going to show you a formula, but I don't expect you to know the formula. You just need to be able to do it using what you know. All right, a couple things I want to point out here. First of all, when we use the LRAM, the left endpoints, what did we get? 14, right? And the RRAM, we got 35? 30, thanks. Is the midpoint the average of these two? No. You might almost expect it to be, but since it's a curve and not a straight line, the midpoint is not going to give us an average. If you look at the picture, and if you had drawn the picture accurately, which I'm not 100% sure that I did, but you can actually see that this right here, this extra piece here, is smaller than this gap right here. So what that means is each one of these, and that's going to be true for each one, what we're going to get here is an under approximation. So this 21 is actually a little bit less than what we would expect. If we were to average them, we would actually get slightly an over approximation. If we take the average, we would get 22. There's a few ways we could look at that, but since it's concave up, that means a straight line connecting the left endpoint and the right endpoint would end up being slightly above the curve, which you can kind of see there with that one. You can see the curve is below it. So if we use that line to find an area, we would get an over approximation. Since the area is going to be somewhere between 21 and 22, then we know it's going to be 21 point something. We still don't know exactly what it is, though. Joe, you had your hand up. Question? Neither the trapezoid, which is the average of the left and the right, nor the midpoint are necessarily more accurate. Again, it just kind of depends on the shape of the curve. If the concavity is changing, then it's going to depend. It's just going to be kind of a toss-up. What we're going to do, though, is we're going to do what, I'm going to go back to this again, what Abdallah and Jeremy suggested, and make more rectangles. And Devin said this at the very beginning, we're going to use a limit and actually make infinitely many rectangles and use that infinitely many rectangles to get an exact area. And that's really the only way to get an exact area. Cole?
Is it like proportionally?
Sigma notation, you guys remember sigma? Adding a bunch of things together. So what sigma means is we're going to go from I equals 1 to I equals whatever n is, and we're going to add each of those terms together. So this right here, this expression means a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. So let's do this real quick. What would be the value we get here? And how would we do it? What are we going to start with? I equals 1, so we put 1 in, we get 1 squared, right? Then we go to 2. We put 2 in, and we get 2 squared. And then we go to 3. And how do we know when to stop? Yeah, when we get to the top number, which is 4, we stop. We actually did this already. We did 1 plus 4 plus 9 plus 16, and we got what? Yeah, that ended up being our RRAM for the last example, right? So you guys remember what the sigma means? Now, we'll get into the sigma in more depth tomorrow when we do Riemann sums. This picture here is exactly the same thing that I showed you earlier. And just to give you an idea of what the formulas look like, again, I don't want you to use these formulas. This is the formula for LRAM. So A is the left endpoint, or the starting point of the interval. Delta x is how wide each of the rectangles is going to be, and we figure that out by taking the size of the interval divided by the number of rectangles. And so we'll take the width of each rectangle times the height of each rectangle, which would be given by this, to get the approximate area under the curve. What we're going to do is we're going to take a formula kind of like this, and we're going to take a limit as n goes to infinity, because n is going to be the number of rectangles here, and that's going to tell us the exact area under the curve. Doesn't that sound fun and exciting?